Salam alaikum wa rahmatullahi wa barakatuh. On va aujourd'hui à l'université 8045 de Guelma, de faculté des sciences et technologies et de la technologie et département d'architecture. On a le plaisir d'assister à une soutenance de thèse de doctorat LND dont l'intitulé est Optimization of Energy Performance through Urban Parametric Design, Case Study of Residential Building in Guelma City. Je ne sais pas laquelle j'étais parfait, je ne sais pas. Hein? L'essentiel, j'ai un défaut de langue là. Ça, c'est l'intitulé de la thèse, présentée par Gergour Hanan, dirigée par Sharatiya Mohamed, docteur MCA, Université 8 mai 1945 Guelma, co-directeur des Cheikh Assoul, aussi docteur et MCA, Université de Msila, co-superviseur, et on a comme invité professeur de Bech Samira, université, voilà, invité extérieur et examinatrice professeur de Bech Samira, l'université 3, Zahbo Bnidel Constantine. Et on a aussi parmi nous un autre expert aussi, et professeur Jamal Alqama, Université 8 mai 1945 de Guelma, et moi-même, professeur Lazali, Université 8 mai 45 Guelma. On va vous allouer à peu près 35 à 40 minutes d'intervention, et on va passer pourquoi j'annonce ça. On va passer au professeur de Bech de l'Université de Constantine parce qu'elle a d'autres aussi, je dirais, travaux à faire. Allez-y, Gergour Hanan.
Thank you, Professor. Greeting everyone, committee members, audience, my colleagues, my family. I'm pleased and honored to present to you our thesis results. Before I start, I would like to present or address estimated thanks to the members of the jury.
Le son. Il fait des coupures.
قبل الميكرو تاعتي فتحي الميكرو ما عندك صاي شوفي تاش سميرة سي بيان اسكو فتحته زي مش قاعده تهضر
هذا معاه انسى دو بارلي هذا معاه
Professor,
encore une phrase correcte
هدري
une phrase correcte allez-y.
so Professor, do you hear me?
الو سميرة يا هدري ديري روحك
So first, I would like to present. During this research, we've been dealing with the theme of the optimization of energy performance through urban parametric design, case study of residential buildings in Guelma City. So to provide a clear roadmap for our.
حاكم كوبيا الميكرو شوفي الميكرو يا سو زرتي منى هي الأوتور تاع اللي تجيري هي اللي قفنا وهذاك شوف ذاك نعيط لزرتي منى دقيقة.
Ça, ce sont les aléas du direct. Difficile.
So to provide a clear roadmap for our research, we established or we can say presentation structure, which progressing from literature review to the empirical analysis. So starting from the introduction and the global context of the study, followed by the problematic, which define the research gap and state the research question. And then our hypotheses and objectives, which define the specific goals of the study, are determined. The core of the defense cover, which is the methodology and the implementation, is determined, and then which leads to the data and analysis. Finally, the results will be presented and finalized by conclusion, recommendation, and perspective for future work. So our research begins by framing the global imperative, which the global trajectory of urban expansion and unprecedented population growth has amplified anthropogenic pressure, leading to a profound climatic and environmental repercussions. The built environment is at the very core of this challenge, contributing a substantial portion of global energy consumption and greenhouse gas emissions. The critical factor in the critical factor is urban structure. We know that the geometrical structure of urban areas determines the ability of building surfaces to take advantage of natural elements, including light, ventilation, and heat, influencing the energy consumption of individual buildings and the entire urban organism. Therefore, the intricate relationship between urban complexity, local climate, and energy consumption demands a context-specific approach to assure energy sustainability in unique climatic settings such as Algeria. So the thesis body is organized into 6 main chapters presented as follows. So chapter 1 sets the theoretical foundation by reviewing existing literature on urban performance, urban patterns, and the interconnection in the co-optimization process. Chapter 2 introduces the concept of parametric design and its application to environmental optimization in the urban context. Chapter 3 focuses on understanding urban climate and its parameters. Chapter 5 analyzes the selected case study. Chapter 6 outlines the results methodology, including the conceptual framework, energy performance optimization throughout climatic and morphological optimization and simulation techniques. Chapter 6 presents the findings of the research, and we finally finalize by a general conclusion, synthesizes the main contribution of the study, identifying the study's limitation, recommendation, and perspectives. So based on the theoretical synthesis of existing literature, energy performance is fundamentally predicated upon 3 parameters, primary design parameters, which are building envelopes attributes, including form, orientation, dimensions, compactness, and material composition. Secondly, we have the urban climatic conditions. And thirdly, we have the morphological configuration of urban areas, which directly affect the outdoor environment. Before presenting the core problem, it is essential to acknowledge the existing framework. Algeria has a clear intention to promote energy transition. This commitment is evident in our robust registration framework. The institutional framework is well defined, led by the Ministry of Energy, supported by key bodies tasked with the policy of implementation and energy rationalization. This signifies a strong national will. However, despite these formidable efforts and resources, a major discrepancy emerges when examining the real-world data. This leads us directly to the central problematic of this thesis. So in the specific national context, this policy to practice gap is actually visible. Despite the push for renewables, our total energy supply remains critically reliant on fossil fuels. The majority of our existing urban fabric, especially residential areas, was constructed without any substantive climatic-aware adaptation standards. This leads to the high energy demand that actively undermines national energy security goals. So therefore, the failure to integrate climate-aware standards into our cities leads directly to the core question driving this inquiry. How do optimized urban environments enhance building energy performance in semi-arid climates? So this single question dedicates the entire scope of our investigation. It necessitates an analysis of 3 main factors. The first, we have identifying the specific urban parameters that matter the most. Second, testing the feasibility of optimization process using a representative semi-arid city, in our case is Galma City. And third, we have developing strategies for integrating our existing energy efficient building stock in a new energy program. To address the critical performance gap, we propose the following central hypothesis. A parametric design approach provides an effective urban strategy capable of co-optimizing energy performance and urban patterns. This is an innovation that moves beyond traditional methods to allow us to simultaneously enhance outdoor thermal comfort and reduce buildings' energy demand. The key concept here is parametric design that allows us to mitigate the limitations of combining disparate data sources, climate, energy use, and urban form to create a newest and dynamic model of urban interactions. So therefore, among the objectives listed in the thesis manuscript, the primary objective of this study is to optimize the energy performance of residential buildings within the context of their physical characteristics and urban morphology. Moreover, this paper seeks to identify factors within the urban environment that contribute to energy loss while investigating the complex interaction between urban spatial configuration parameters and performance indicators. To provide a comprehensive overview of the research methodology and test the hypothesis, this research employs a rigorous, we can say, a scenario-based analysis throughout a two-phase deductive framework. The entire process is centered on parametric modeling and simulation, allowing us to effectively test numerous selected urban geometry cases. Urban energy consumption is highly tied to climate conditions. To this end, phase 1 is dedicated to characterizing the baseline climatic status of the study, area using rhinoceros and grasshopper, especially within the Ladybug plugin based on energy plus weather file input, to conduct solar analysis and define key urban parameters. The second phase focuses on analyzing the urban microclimate in Galma, structured into steps. First, we have data collection, involves analyzing the city's physical morphology, including buildings form, density, street canyon, and vegetation, to construct a detailed 3D model demonstration using AutoCAD and Google Earth and NVMe Spaces tool. So, crucially, field measurements were conducted using a deep point aggregator to gather air temperature and relative humidity, and an enumerate model BA16 to quantify wind speed, all serving a vital input for urban weather modeling. And the second phase here is simulation utilizing the NVMe suite, which is NV Core. Phase 3 then translates the findings of Phase 2 to the building level to assess energy performance. This is where our parametric approach comes into full effect. This framework merges the two critical data streams, which are real-world energy use data sources from building utility meters, and with the digitally constructed architectural model built in Revit 2025. The building precise geometry from Revit alongside the contour readings provides the primary input for the energy simulation software, which is OpenStudio. It is a 3D, we can say, presentation of Energy Plus software. So to summarize the entire process, this figure illustrates our deductive research workflow. Collecting in-situ measurement and urban geometry data informs our NVMe simulation to quantify outdoor thermal comfort. The results from Phase 2 directly inform Phase 3. The final step is to compare the outcomes against existing data. This comprehensive findings comparison is what ultimately allows us to generate our evidence-based recommendations to further inform urban planners. So after presenting our hypothesis and the corresponding method, our framework must be rigorously tested within a relevant and representative environment. This leads us to the selection of the case study. Our chosen case study is Galma City. Galma is structurally representative of the challenges facing Algeria's urban development for three crucial reasons. First, climatic relevance. Galma experiences the full range of semi-arid climate characterized by significant temperature fluctuations and intense solar radiations. This make it an ideal testing ground for strategies aimed at mitigating heat stress and reducing cooling loads. Secondly, we have its urban typology. The city features a high concentration of precise residential typologies that are, we can say, disproportionately contributing to the energy consumption, a problem we already highlighted. Third, we have the policy application. Success in Ghana demonstrates the feasibility of applying our findings to numerous similarly situated cities, maximizing the impact of this research on a national scale. So the study area that we chose is the South Land Use Plan in Ghana, which was designed to reveal conjunctions in the city center. The analysis focuses especially on the new prevailing mid-rise building typologies, a shift from the historical low-rise structures because the area is inhabited, allowing for the collection of real-world microclimate data essential for validated simulation models. So the implementation phase of the research centered on optimization by systematically manipulating urban morphological parameters, which are urban form, urban density, and we have the building orientation. The second group involves the climate parameters, including a detailed air temperature data, wind speed, and relative humidity. This synthesizes of precise design parameters and validated environmental parameters is the foundation of our urban climate modeling and simulation phase, ensuring our optimization study is grounded in the real microclimate conditions of the selected area. With our morphological and climatic parameters defined, we moved into the core of the methodology, which involves two integrated simulation phases, beginning with the urban climate modeling, and the investigation focused on the urban energy modeling to define the correlation between urban spatial arrangement and energy utilization by collecting and comparing real-world energy consumption data from representative buildings across different urban configurations. So, having established a rigorous two-phase simulation framework, we now move to the findings, which are the empirical evidence that answers our research question. So the central objective of this thesis was to answer how do optimized urban environments enhance buildings' energy performance in semi-arid climates. Our results directly validate our hypothesis, which is that a parametric design approach can significantly co-optimize thermal comfort and energy demand. The findings are presented in two distinct yet interconnected parts from the urban climate optimization result and the urban energy performance results. We will now proceed to the presentation of the empirical findings, commencing with the quantified impact of urban morphology on the microclimate conditions of the south area. Our initial phase involved in situ measurement, as we see in the presentation, across representative hot and cold periods. The purpose was twofold. The first is to capture the true thermal behavior of Ghana's environment and to generate accurate localized data for our simulation inputs. Field measurement during the hot periods revealed a significant moderation of effect of vegetation, which lowered the air temperature by, we can say, 8.4 degrees, from a peak of 46 degrees up in areas to average of 37.16 under cover, and reduced wind speed also. However, relying slowly on these direct measurement is insufficient for a comprehensive evaluation of thermal perception and of optimization. Consequently, the collected data, particularly the measurement of air temperature, relative humidity, and wind speed, was utilized as the ground input to validate the urban climate modeling. So following the validation of our local microclimate throughout in-situ measurement, we proceeded to the urban climate and simulation to our three distinct urban configurations to quantify their thermal performance. So the slide representing the scenario 1, which is a courtyard enclosed urban form in cold periods and in hot periods. So scenario 1, characterized by the closed courtyard and north-south orientation, revealed a significant internal heat trapping effect. While scenario 2, featuring a linear typology and significantly wider street canyon, exhibited a different thermal distribution. The maximum potential air temperature was concentrated in the northern section, reading 36.9 degrees at pedestrian height, which is 1.4 meters, which is higher than the average temperature recorded in scenario 1, which was 35 degrees. This can be attributed to the denser surrounding buildings and the prevalence of low albedo materials. The wider street canyons allows more sunlight to reach the ground, contributing to higher heat absorption and subsequent radiation at different heights. Despite the heat, the wider canyon did improve air circulation, resulting in elevated wind speed during the cold winter period, demonstrating its potential for heat dispersion under different seasonal conditions. Scenario 3, with its east-west orientation, revealed distinctive patterns of thermal stability and exposure. The build geometry resulted in a more stable distribution of potential air temperature compared to scenario 1 and scenario 2. However, this stability results from the urban configuration's tendency to expose the surrounding outdoor areas to direct weather variation in both summer and winter periods. While minimizing internal hotspots, it fails to provide the same level of microclimate condition as the first scenario. So based on the combined simulation results, we draw the following conclusion regarding thermal comfort optimization. First, we have the morphological effectiveness. The findings confirm the decisive interplay between microclimate data and urban design element, namely form, orientation, and urban canyons. Secondly, we have the optimum orientation. Overall, the north-south orientation appears the most advantaged regarding the two other orientations. In regard to the urban conflict, the closed courtyard, which is scenario 1, while minimizing radiation, it creates a trapping heat effect, which leads to the urban heat effect. So, a crucial role of a green infrastructure, the necessity of prioritizing green infrastructure is strongly underscored. As we already mentioned, that it reduces the heat to 8.4 degrees. So these climate optimization results now serve as the foundation for the next step, which is quantifying the impact of these optimized scenarios on buildings' energy consumption. To validate the prediction from our thermal sensation simulation, we conducted a quantitative analysis using real-world energy utilization data. So building A, which is located in scenario 1, represents high consumptions, energy consumptions. Building A consistently exhibited the highest consumption with several individual units exceeding 15,000 kilowatt per hours. While building B, which is located in scenario 2, moderate consumptions, which characterized by moderate consumptions. So building B showed moderate reductions with a total consumption of 96.4 kilowatt per hours, while building C, which is located in scenario 3, demonstrated the lowest energy usage, recording a total of 53.9 kilowatt per hours. So the most critical finding is the strong and direct correlation of urban configuration and urban or building form to energy consumption. The quantitative analysis of real-world energy consumption validates the core promise of this research, which is different urban configuration diametry result in varying energy demands. So we now proceeded to the final step, which in our analysis, which is quantifying the energy consumption throughout simulation. So we did an in-situ simulation, energy simulation, using data from building counters, and then we use Revit and OpenStudio, which is a 3D representation of Energy Plus, to compare these two types of approach in the energy consumption or the energy simulation analysis. So the present figure represents building 1 in scenario 1, and then the second approach for building B, which is a linear north-south in scenario 2, and building C, which is a linear east-west in scenario 3. Both linear buildings were simulated to have a higher cooling demands regarding to scenario 1. So dominance of the cooling loads. Throughout this simulation analysis, we observed across all buildings there is a significant reliance on cooling for far surpassing heat needs. So buildings A, for example, showed a cooling consumption of 778 kilowatt per hour, 78,000 compared to distinct heating consumption of 6.9 kilowatt per hour in the two simulated buildings. So in sum, the simulation predicted that the courtyard buildings, which is a building A, would be the most energy efficient due to the passive solar protection. So despite the accurate methodology framework that we did, the empirical counter readings revealed a critical divergence from simulated prediction, with building A consuming the highest energy contrary to the model's projection of the lowest. This disparity affirms that real-world performance is shaped by factors often omitted in simulation environments, which we attribute to four main causes. The first cause is the temporal difference and degradation. Building in scenario 1 was inhabited in 2017, while the two other scenarios were inhabited in 2019. The second is the microclimate amplification, where the courtyard design intensified heat gain beyond the model's prediction. The third is occupant behavior. And finally, we have data limitation, as the total energy counter data could not isolate heating and cooling loads that were to sole focus of the simulation. These findings highlight the necessity of integrating real-world constraints, for example, equipment age and human factors, into future urban energy models to bridge the gap between prediction and reality. So we have traversed the full cycle of our investigation, from establishing the policy gap and validating the local microclimate to simulating and measuring the energy performance of various urban forms. We now arrive at the conclusion which synthesizes the intricate relationship between urban morphology and energy demand. The study confirms a strong and indirect correlation between a building's thermal behavior and its energy consumption. Elevated potential air temperature and increased solar exposure consistently drive higher cooling demands. The comparable energy consumption between the north-south orientation, which is scenario 2, and the east-west orientation in scenario 3, or linear forms, emphasizing the substantial impact of orientation on cooling requirement in semi-arid environments. To conclude, this research investigated the intricate relationship between urban design parameters and energy performance, allowing us to directly address the critical gap in local urban planning practices within Algeria. Our core objective was to validate the central hypothesis, which is a parametric design approach can provide an effective urban strategy capable of enhancing outdoor thermal comfort and significantly reducing building energy demand. The findings presented throughout the result provide a compelling evidence supporting this hypothesis. By employing parameterization, this research overcomes the limitation of traditional methods, successfully generating a more nuanced and dynamic model of complex urban interaction that previously not possible for creating climate resilient and thermally comfortable urban spaces in challenging semi-arid environments, and ultimately contributing to the development of more sustainable and energy efficient cities. Simulation and modeling refinement. Future studies, now we move to the recommendations. So future studies must employ, for example, longer simulation periods. In our case, we only used 10-hour simulation period. So a 24 simulation period could have different results. Additionally, there is a necessity to explore more detailed urban models. Second, concerning data collection accuracy, the inability of current energy counters to differentiate between heating, cooling, and other electrical loads can lead to an overestimation of thermal demands. Future work must explore a method to isolate and accurately measure these specific energy components. So, furthermore, the significant influence of occupancy patterns necessitate acquiring accurate, detailed data on occupant space schedules and occupant use, which are inherently difficult to, we can say, to analysis in the model or the parametric models. Third, on data quality, the accuracy of simulation tools fundamentally depends on the quality of the input data. Therefore, careful attention to the capability and reliabilities of data collection measurement is crucial for robust simulation outcomes. Moving now to the perspectives of our research. So although our research applies specifically to Galma City, they have significant implication for global urban planning. Cities in the Mediterranean arid regions facing similar climatic challenges such as Galma can implement the strategies outlined in this study to improve their thermal comfort and sustainability. Finally, to broaden the scope of this research, future investigation will prioritize a systematic, comprehensive approach. This systematic approach shift is essential as individual buildings assessment fail to capture the complex or the emergence behavior within the urban environment as a whole. Future analysis will also leverage modeling tools that rely on granular microclimate data rather than broader methodological readings. This methodological readings refinement is necessary to deliver the most precise and contextually relevant understanding of urban dynamics. So, at the end, thank you so much for your time and attention, and I hope I was able to provide a clear, understandable overview of our work, and now I'm ready for any observations or guidance regarding our research, and thank you so much another time.